With aromatic hydrocarbons. Okay, so aromatic hydrocarbons are also known as arenes. They have pleasant odor, and therefore they are also, in Greek words, they are called as aroma, meaning pleasant smell. The class of compound was named as aromatic compound. Most of such compounds were found to contain benzene rings. Okay, so many of the aromatic compounds were found to contain this benzene. Benzene ring is highly unsaturated, means there is presence of double bond. But in the majority of reactions of aromatic compounds, the unsaturation of benzene rings is retained. Okay, so like if we talk about the reaction of aromatic compounds, the unsaturation of benzene ring is present after the reaction with those compounds. However, there are examples of aromatic hydrocarbons which do not contain a benzene ring, but instead contain a highly unsaturated ring. Okay. So they do not contain a benzene, but still they have a highly unsaturated ring. So aromatic compounds containing benzene ring are known as benzenoids, and those not containing benzene ring are called as non-benzenoids. Some examples of arene are as follows: benzene, toluene, and aniline. First is our benzene, which is C6H6. Then comes toluene and aniline. C6H6 is a six-membered ring having alternate, double, and single. Toluene is alternate, double, and single bond with methyl group attached on it. Aniline is the alternate, double, and single bond with NH2 group attached on it. This is aniline. So nomenclature and isomers. The nomenclature and isomerism of aromatic hydrocarbon we have discussed in unit 12, that all the 6 hydrogen atoms in benzene are equivalent. So it forms one and only one type of monosubstituted product. Okay. When 2 hydrogen atoms in benzene are replaced with 2 similar or different monovalent groups or atoms, 3 different position isomers are possible. Okay. Okay, so 3 different positional isomers can be ortho, meta, and para. So if it is at 1,2 position, it is ortho. If it is at 1,3 position, it is meta. If it is at 1,4 position, then it is para. Okay. 1,2 or 1,6. Okay. So like 1, 2, 3, 4, 5, and 6. Okay. So 1 and 2 and 1 comma 6 or 1 comma 6 will be our or 1 comma 3 or 1 comma 5 will be our meta, and 1 comma 4 will be our para. Okay. 1 comma 3 and 1 comma 5 will be our meta, and 1 comma 4 will be our para disubstituted. Okay. So like we have seen that orthoxylene is when 2 methyl groups are attached. Okay. So it is ortho at 1,3 position. It is meta if they are attached at 1,3, like it is ortho if it is attached at 1,2 position. Metaxylene if 2 methyl groups are attached at 1,3 position. Paraxylene if 2 methyl groups are attached at 1,4 position. Ethyl benzene is when CH2, CH3, or we can say C2H5 is attached to benzene. 1-chloro-3-methyl benzene. You know that 3-methyl benzene, like this methyl benzene is known as toluene. And 1-chloro at first position there is fluorine group, and then comes at the first, second, and third position there is methyl benzene. Okay. So Friedrich August Kekule, a German chemist, was born in 1829. This is how the benzene was founded by Friedrich August Kekule. So at Darmstadt in Germany, He became a professor in 1856 and followed Royal Society in 1875. He was the fellow of Royal Society. And he made major contribution to structural organic chemistry by proposing in 1858 the carbon atoms can join to one another to form chain. And later in 1865, he found an answer to challenging problem of benzene structure. That because of resonating structure, he gave the resonance that how the benzene can exist. This double bond can shift over here. Okay. By suggesting that these chains are close to form the rings. Okay. These chains can close to form a ring. He gave the dynamic structural formula to benzene, which forms the basis of the modern electronic structure. Okay, so based on his structure, which was given in 1965, the modern structure is similar. He described the discovery of benzene structure. He was sitting, writing his textbook, but the work did not progress. His thoughts were elsewhere, and then he turned his chair to the fire and dozed. And that is why, in his dream, this calculus structure of benzene came. Okay. So while he was thinking and again, and then suddenly the structure of benzene, he was thinking about the conformations, various conformations, long rows, sometimes more closely fitted together, all twisting and turning into a snake-like motion. Okay. So then he came to the structure of benzene, okay, calculus structure. That is why they are also known as calculins. Structure of benzene. Benzene was isolated by Michael Faraday in 1825. Okay, so he gave the structure of benzene in 1865, but it was isolated by Michael Faraday in 1825. Okay, so after 40 years, the structure of benzene, that how it forms the resonating structure, was discovered. The molecular formula of benzene is C6H6, indicates a high degree of unsaturation. Okay, it is having 3 double bonds. This molecular formula did not account for its relationship to corresponding alkanes, alkenes, and alkynes. Like alkanes were having the molecular formula of CnH2n plus 2, CnH2n and CnH2n minus 2. Okay, so these formulas were not applicable for benzene. So it is having the structure, it is having the unique property and unusual stability. Okay, so like it took several years for scientists to assign the structure. Okay, so it is the stable molecule and found to form a triozonoid, which indicate the presence of 3 double bonds. Benzene was further found to produce one and only one monosubstituted derivative, which indicate that all the 6 carbon and 6 hydrogen of benzene are identical. Okay, so if I talk about this, all the 6 carbons and 6 hydrogens are identical. Okay. On the basis of this observation, August Capel in 1865 proposed the following structure of benzene, having cyclic arrangement of 6 carbon atoms with alternate single and double bonds, and 1 hydrogen atom attached to each carbon. Okay. The calculus structure indicates the possibility of 2 isomeric 1,2 diaminobenzene. Okay. 1,2 diaminobenzene. In one of the isomers, the bromine atoms are attached to the doubly bonded carbon atom, whereas in the other, they are attached to a singly bonded carbon atom. So, like if we talk about the 2 isomers, the bromine atoms are attached to the doubly bonded carbon atom, whereas in the other, they are attached to singly bonded. So, like here, they are attached to doubly bonded. Here, they are attached to singly bonded carbon atom. This one is single. So, these are the 2 resonating structures of benzene. However, benzene was found to form only one ortho disubstituted. Okay. So benzene was found to form one ortho disubstituted product. This problem was overcome by calculus by suggesting the concept of oscillating nature of double bond in benzene. Okay. So even like we have discussed that these are the oscillating two structures of benzene. These double bonds are oscillating. Okay. They are changing their position. So if they will change their position, it will become like this. If it will change its position, then the second structure can be formed. Okay. Even with this modification, calculus structure of benzene failed to explain the unusual stability and preference of substitution reaction. Okay, that why the substitution happens then addition reaction, which could later be explained by resonance. Okay, so resonance and stability of benzene. According to valence bond theory, the concept of oscillating double bond in benzene is now explained by resonance. Okay, so benzene is a hybrid of various resonating structures. The two structure A and B by calculase are the main contributing structure. The hybrid structure is represented by inserting a circle or a dotted circle in the hexagon as shown in C. So here we are having these calculus structures in which this, so the double bond will come here, here and here. Okay. And if we again make this structure, then the double bond will come here, here and here. So this is what the resonance hybrid, okay, or the calculate two equivalent resonating structure of benzene fluoride. So the hybrid structure is represented. We have seen that in the C, the hybrid structure was represented with a dotted circle in the hexagon. The circle represents the 6 electrons which are delocalized between the 6 carbon atoms of the benzene. So this circle is representing the 6 electrons. Okay, so these are the 1, 2, 3, 4, 5, and 6. These are the 6 electrons which are delocalized. Okay, so they are delocalized. So a circle is there so as to represent the delocalization of these electrons. The orbital overlapping gives us a better picture about the structure of benzene. So if there will be orbital overlapping, okay, so this benzene is having the like carbon, if we say that CH bond is present. So each carbon is having the p orbitals. Okay, so the pp overlapping between the orbitals, like here if we say so that is why the double bond formation is there. Oh, alternatively, there is double bond formation, okay, in the benzene. So first of all, there is this and this pi bond formation, and this pi bond formation, and then here between the two structures there can be a pi bond formation, like between this carbon and this carbon, this carbon and this carbon. Okay, so alternatively there are three pi bond formation which is taking place in benzene. Okay. Okay, so all the 6 carbon atoms in benzene are sp2 hybridized. We know that double bond stands for sp2 hybridization. Two sp2 hybrid orbitals of each carbon atom overlap with sp2 hybrid orbital of the adjacent carbon atom, make 6 cc signals. Okay, so like each carbon atom is having p orbital. They overlap to form pi bond over here, here, and here. Okay, to form 6 cc sigma bonds which are in the hexagonal plane. The remaining sp2 hybrid orbitals of each carbon atom overlap with s of the hydrogen atom to form 6 ch sigma. Okay, so here the carbon atom is overlapping with hydrogen to form 6 ch sigma bonds. These are various sigma bonds. 6 sigma bonds are present. Okay. Each carbon atom is now left with one unhybridized p orbital perpendicular to the plane of the ring as shown below. Okay. So now here each p orbital was left with the each carbon atom was left with the p orbital which was perpendicular to the plane. We can see here this is perpendicular to the plane. The unhybridized p orbital of carbon atom are close enough to form a pi bond by lateral overlap. So structure correspond to two calculus structure with localized pi bonds. The internuclear distance between all the carbon atoms in the ring has been determined by the X-ray diffraction to be the same. Okay. So means if there is overlapping or the internuclear distance between these two carbon atoms is found to be same. All this distance is found to be same. Of p orbitals by X-ray crystallogram. Okay. There is equal probability for the p orbital of each carbon atom to overlap with the p orbital of adjacent carbon atom. Okay, so this can be represented in the form of two donuts ring on the of the electron cloud. Okay, so if I'm having this carbon atom, this benzene ring, then two donut. Okay, so one is above and one is below. One above and one below the plane of the hexagonal ring. Okay, so the like I have mentioned here that this can be the donut structure, which can be one below and one above the benzene. Okay. So the unhybridized p orbital of carbon atom are close enough to form a pi bond bilaterally. So these p orbitals are very close enough to form a pi bond by the lateral overlapping. There are two equal possibilities of forming a three pi bonds by overlap of p orbitals C1, C2, C3, C4, C5, C6, or alternatively C2, C3, C4, C5, or C6, C1 respectively. Okay, so one can be 1, 2, 3, 4, and 5, 6. One can be 2, 3, 4, 5, and 6, 1. Okay. So these are the two probabilities which can be possible. So the 6 pi electrons are thus delocalized and can move freely about the 6 carbon nuclei instead of any. The delocalization of pi electron cloud is attracted more strongly by the nuclei of the carbon atoms than the electron cloud localized between two carbon atoms. Okay. So these electrons, 6 electrons, 6 pi electrons are thus delocalized. Okay, so they can be in resonance and can move freely about the 6 carbon nuclei instead of any two. Okay, so they can move freely. The delocalized pi electron cloud is attracted more strongly. Okay, and this delocalized, like they can move freely. So this delocalized pi electron cloud is attracted more strongly by the nuclei of the carbon atoms. Okay, then the electron cloud localized between two carbon atoms. So like these two carbon atoms are having an electron cloud which is less repulsive as compared to the delocalization of the electrons. Okay, so the delocalized pi electron cloud is attracted more strongly by the nuclei of the carbon atom. Okay, so the nuclei of the carbon atom attract these electrons. Then the electron cloud of the localized carbon atom. Okay, so localized are less reactive. Okay, so they are not strongly attracted by the carbon. Therefore, presence of delocalized pi electron in benzene makes it more stable than the hypothetical cyclohexatriene. Cyclohexatriene is when you are adding three double bonds, okay, but they are localized. But in benzene, they are delocalized. They are in resonance, okay, and they can move freely. So X-ray diffraction data has revealed that benzene is a planar molecule, that it is having the sp2 hybridization. Had any one of the above structure of benzene, A or B, be correct, two types of CC bond length were expected. Okay. However, X-ray data indicate that all the 6 carbon bond length are same order. Okay. We have seen that all the CC bond length in benzene, 6 CC bond length, are equal of 139 picometer, which is intermediate between CC single bond 154 picometer and CC double bond 133. Thus, the absence of pure double bond in benzene occurs for the reluctance of benzene to show addition reaction. Okay. So if pure double bond is not there in benzene ring, okay. So therefore, reluctance of benzene to show addition reaction. That is why it does not show addition reaction under normal condition, thus explaining the unusual behavior of benzene. So due to the absence of pure double bond, localized double bond, it does not show addition reaction. Aromaticity. Okay. So benzene was considered as parent aromatic compound. Now the name is applied to all the ring system, whether or not having benzene ring possessing following characteristics. Okay. This is given by Huckel's rule. Huckel's. So this is called as Huckel's rule. First, it should be planar sp2 hybridized. Complete delocalization of pi electrons. They should be able to move. Like if we draw a benzene structure, presence of 4n plus 2 pi electrons when n is an integer. Okay. So benzene is having 6 pi electrons. 1, 2, 3, 4, 5, 6. Okay. So 4 into 1 plus 2 is 6. Okay. So if we take the example of naphthalene, it is having 2, 4, 6, 8, 10, 12 pi electrons. Okay. So 4 into 2 plus 2 is 10 pi electrons. Okay. So like it is having here, it is not having a double. So it will be 10 pi electrons because it's in conjugate. Okay. So like double, double, single, double, single, and then here it will be a double. Yes, the double bond will be present over here, so it will be 10 pi electrons. So it is aromatic. Okay. Then anthracene is having a 3-membered structure, ring structure. 6, 10, and then 14 pi electrons. Then how 4n plus 2 pi electrons? What should I substitute for n so that I get 14? Okay. It is where n is not the number of rings. Okay. N is not the number of rings. It is just a coincidence that here the number of rings are 3, here the number of rings are 2, and here the number of rings are 1. Okay. So we just have to find that how many pi electrons are there, and on that basis we will find that 12 plus 2, which is 14 pi electrons should be present. So on the basis of the number of pi electrons which are there, on that basis we'll put the value of this integer. Okay. This is often referred to as Huckel rule. Okay, this is Huckel rule. Some example of aromatic compounds are given below: naphthalene, anthracene, and phenanthrene. Okay. So, like this was the structure of phenanthrene. Similar structure is there for anthracene and phenanthrene. Just if the three-membered ring, third one is attached above, then it will be our anthracene, then it will be our phenanthrene. And if the planar straight ring is attached, then it is our anthracene. Okay, so one membered ring is called as benzene. Membered ring is called as naphthalene. Three-membered ring is called as anthracene, or we can say it as phenanthrene. Okay, then preparation of benzene. Benzene is commonly isolated from coal tar. Okay, so we know coal tar is carbon containing compound. However, it may be prepared in the laboratory by the following methods. So, cyclic polymerization of ethine. If I take the three molecules of ethine, then due to the cyclic polymerization, benzene can be formed from ethine molecule. Decarboxylation of aromatic acid. Sodium salt of benzoic acid. So if I take this is called as my benzoic acid, COH. If I have to make it sodium salt, then I will react it with sodium. So this will be COONA with the removal of this H and this H. So this will be H2O. Sodium salt of benzoic acid on heating with soda lime. Soda lime is my calcium oxide and NaOH. Okay. With soda lime gives benzene. Sodium hydroxide and calcium oxide. And this this NaCO2, CaCO3 is removed. And this NaOH is also removed, giving us benzene. This is called a decarboxylation because it is happening due to the removal of carbon dioxide from the molecule. Okay. So we know that decarboxylation reactions are those in which carbon dioxide is removed from the molecule. Okay. And soda lime is our NaOH and CaO molecule. Sodium hydroxide and calcium oxide gives us soda lime. Okay. So this sodium carboxylate ion, okay, benzoate, sodium benzoate. This is a bit. Sodium benzoate when on reaction with soda lime, sodium hydroxide, and calcium oxide. So calcium oxide has the tendency, okay. This CaO will remove this CO2, okay, in the form of CaCO3, okay. CaCO2 and O is CaCO3, calcium carbonate. And here this benzene ring in the presence of sodium. Okay, so this sodium will be removed. Okay, NaOH will be. Okay. So we'll get this benzene ring. So by the decarboxylation of aromatic acids, then reduction of phenol. Phenol, we know that when alcoholic or hydroxy group is attached to benzene ring, it is called as phenol. In presence of zinc dust, when heated at high temperature, it is removed in the form of hydroxide. Zinc oxide is formed. It is removed in the form of oxide. Zinc oxide is formed and benzene ring is with alternate double and single bonds. Then various physical properties of benzene. Okay. So aromatic hydrocarbon are non-polar molecules and are usually colorless. Okay. So they are non-polar, first of all. Very important property that they are non-polar. Okay. So benzene, naphthalene, anthracene, these all are non-polar and usually colorless liquids or solids with a characteristic aroma. Okay. They are aromatic. Aromatic means they have a characteristic aroma. Okay. We are also familiar with naphthalene balls, which are used in toilets for preservation of clothes because of their unique smell of the compounds and moth repellent. Okay, they are moth repellent. Aromatic hydrocarbons are immiscible with water but are readily miscible with organisms. Okay. They are immiscible with water because they are non-polar and therefore they are miscible with organic solvents. They burn with sooty flame. Okay, they burn with a sooty flame, which is responsible for their characteristic properties. So, because carbon is evolved, okay, sooty flame is given because carbon is evolved. In chemical properties, arenes are characterized by electrophilic substitution reaction. Okay, they do not undergo addition reaction because of the alternate double and single bond conjugation is present. However, under special conditions, they also undergo, and due to a high temperature if we supply or at low pressure, can undergo addition and oxidation reactions also. Okay. So we look for the various reactions.